Hello, remote students. We're going to start today on page 146, and then you will find a handout at the bottom of, underneath the, or probably on top of the classroom video, and then you have your homework questions. There'll be 10 homework questions. We're talking about what is energy. So we're starting on page 146 in your science book, okay? All right. If you look at that picture there at the top, we discover activities. It talks about dropping a tennis ball from different heights. Everybody, I think, has probably figured out that, you know, if you drop a tennis ball from right here, it's not going to bounce as high as if you drop it from up here, okay? Because it picks up more momentum and the speed and everything. Even though it weighs the same, the ball doesn't, the weight, the mass of it doesn't change. But as it hits, it will exert more energy and more speed it has picked up, okay? And that's what that little experiment is. Probably next Friday morning, we'll have probably very short classes because it's a half a day. We'll do a few of those little experiments and things like that. Yes, Caleb.
So I saw this video where they had a basketball and a tennis ball, and then you dropped them at the same time.
Yeah.
And the tennis ball went like 30 up feet. Really high.
Yeah.
And that's I'm pretty sure he said it's because the tennis ball's energy was multiplied by the basketball.
It is, and we watched that. We watched that in class. Talking about when we took the basketball, you put a tennis ball on it, and then you put another ball on top of that. Eventually, a basketball, tennis ball, and something else like a super bouncy. And as you drop it, if you can get it to all line up and fall at the same time, it transfers that energy. The basketball will bounce up. The ball on top of it will actually go higher, and then the super bouncy ball thing will take off and go 30, 40 feet in the air. We watched that video, but that's a transference of energy. That's what, and we'll talk about that a little bit later on too. Okay, now here we go. Leo, Brady. All right, brilliant streaks of lightning flashes across the night sky. The wind howls, thunder cracks and rumble. There's a sound like a runaway locomotive approaching, growing louder each second. If you're ever in your house and you hear that and you don't live near a train track, you probably want to get under something nice and sturdy because that usually is a tornado coming at you, okay? Whirling wind rushes through the town. Roofs are lifted off of buildings. Cars are thrown around like toys. Then in a minute, the tornado is gone, okay? The next morning, a light breeze carries past the debris. The wind that destroys buildings hours before is now barely strong enough to move a leaf, okay? Wind is just moving air, but it has energy, okay? When wind moves a house or even a leaf, it causes a change. In this case, the change is the position of the object, okay? Remember, work is done when a force moves an object through a distance, okay? The ability to do work or cause change is called energy. So the wind does indeed have energy. Okay? Work and energy. Okay? When an object or living thing does work on another object, some of its energy is transferred to that object. Okay? You can think of work then as a transfer of energy. When energy is transferred, the object upon which the work is done gains energy. Okay? And energy, of course, is measured in joules, which is the same unit that is used to measure work. Okay? Now, remember, if you remember when we talked about work earlier, you go back and you push against that wall for 20 minutes. Scientifically, you've done no work because you did not move the wall. Okay? You did not transfer any energy to that wall because the wall didn't move. If you try to walk out that door and you put your hands on the door and you push, what happens?
It moves.
Door opens. Door moved. Therefore, you transferred energy to that door. Okay? Kind of see where we're headed here? Yeah, it can get a little confusing if you're not careful, but it's not incredibly hard if you just take your time and think through it for a second. Okay? Power and energy. You can recall that power is the rate at which work is done. Okay? If the transfer of energy is work, then power is the rate at which that energy is being transferred. Okay? The tornado versus a gentle breeze. Okay? Both have energy, just one has a whole lot more power. Okay? So power equals energy transferred over time. Okay? So power is involved when energy is being transferred. For example, a calm breeze. Breeze's power is the rate of energy transferred to lift a leaf a certain distance. The tornado, in that picture right there, transferred the same amount of energy when it lifts the leaf the same distance. However, the tornado has a greater power than that little breeze, so it will transfer it in less time. Okay, the gentle breeze might pick it up and blow it from this wall to that wall, and it might gently ride the breeze and just, eventually get over there and fall back to the ground. A tornado will pick it up here and drive it through a tree in just a matter of seconds over here, okay? A lot more power, okay? Same energy to move the leaf, just more power. And the more power, the faster it will make it go. Yes?
Did you say a tornado can drive a leaf through a tree?
Mm-hmm.
That's scary. A leaf?
I don't know if it can actually drive a leaf. I did say that. I don't know if it can actually drive a leaf through a tree. My guess is the leaf would crumble and break. But
if that was true,
apparently he got your attention, so my purpose here is done. Okay, so no, I doubt seriously if you do that.
Probably a rock.
Or a rock, something like that. Something that wouldn't crumble when it hit something solid. Yeah. But thanks for calling me out on it. All right, kinetic energy. Two basic kinds of energy are kinetic energy and potential energy. Okay, you've heard of both of those, I guarantee it. Whether energy is kinetic or potential depends on whether or not the object is moving. Okay? A moving object, such as the wind, can do work when it strikes another object and moves it some distance. Because the moving object does work, it has energy. And that energy an object has due to motion is called kinetic energy. So kinetic energy is movement. Okay? If something is moving, that is kinetic energy. Okay? All right, everybody got that one? That one's pretty simple. Pretty simple. The kinetic energy of an object depends on both its mass and its velocity. Okay? Kinetic energy increases as mass increases. Okay? Think about it. You get hit by a guy on a bicycle going 20 miles an hour, it's going to knock you down. Okay? You get hit by a bus going 20 miles an hour, it's going to knock you down further. Okay? It's going to move you on down the road a path. Okay? So you kind of see, because they're both going 20 miles an hour, so basically you were hit with the same amount of energy, but the bus weighs a whole lot more than the guy on the bicycle. Okay? So he's going to do more damage because he has more power. Okay? Everybody kind of picking up on that? Okay. Think about a bowling ball. If you roll a bowling ball and a golf ball down a bowling lane, you throw them at the exact same velocity. Yeah, the golf ball is still not going to do a whole lot of damage to those bowling pins. Okay? Bowling ball is going to knock them down because it has more mass. Even though it's going at the same speed, the mass comes into play there. It has more energy, okay, more power. Same energy, more power, excuse me. Yes?
So, my dad experienced a tornado when he was like my age, and he said that there was this like huge tree in his front yard, and it had really big roots. He said that it was on this, like this is his house, it was right here. At the end of the tornado, it was on the other side of the road.
Yeah. Yeah, tornadoes are very powerful. I have gone to areas after they have gone through and seen, I mean, big steel beams, that help building, and they just twisted like
they threw them around like it was a piece of paper.
Yeah, like nothing. Yeah, I mean, it's amazing the power that those things will generate. Okay. All right. Now then, calculating kinetic energy. There's a there's always a mathematical relationship between kinetic energy, mass, and velocity. To get kinetic energy, it's 1/2, okay, just 1/2, times mass, times the velocity squared, okay? That is the formula for calculating kinetic energy. Do changes in velocity and mass have the same effect on kinetic energy? No. Changing the velocity of an object will have a greater effect on the kinetic energy than changing its mass by the same factor, okay? And this is what we're talking about. This is because velocity is squared in the kinetic energy's equation. For instance, doubling the mass of an object will double its kinetic energy, but doubling its velocity will quadruple its kinetic energy, which is about 4 times. Okay? So you can see the velocity play comes into play too. Okay? Hence the tornado. Okay? Potential energy. An object does not have to be moving to have energy. Some objects have stored energy as a result of their position on shapes. When you lift a book up to your desk from the floor, or you compress a spring to maybe to wind up a toy, you transfer that energy to it. Okay? The energy you transferred is stored or held in readiness. It might be used later when the book falls to the floor. Okay? So you're giving that book energy. When you pick it up out of your book bag off the floor and you lay it on your desk, you just gave that book some energy. It's potential energy. Okay? Because if you was to hit it and it falls off your desk, now it is exerting energy as it falls to the floor. Once it hits the floor, kinetic energy comes to a stop and it goes back to potential energy, and it would lay right there. If no one picks it up or kicks it or whatever, it would lay right there until some outside force moves it. Okay? But it's got potential energy. It's got the potential to be moved. It's just not going to move itself. Okay, that can get a little bit more confusing. Okay? So potential energy is when something is not actually moving. It's got the potential to move. Okay? Gravitational potential energy, okay, or GPE. The gravitational potential energy is an object is equal to the work done to lift it. Okay? And remember, work equals force times distance. So the force you use to lift the object is equal to its weight. The distance you move the object and it is its height. You can calculate an object's gravitational potential by using the formula of weight times height. Okay, that will give you the gravitational potential energy. For example, and it gives you an example, the red sphere up here on the left, up in the picture on top of the page, weighs 500 newtons. If the ski jump is 40 meters high, then the skier has 500 newtons times 40 meters, or 20,000 joules, okay, or of gravitational potential energy. Okay, again, if he's just sitting up there on the top of that thing, he really is not exerting energy at that point in time. Okay, until he starts to move, he has potential energy. Okay, the more an object weighs, or the greater the object's height, the greater its gravitational potential energy at the same height. Okay, a 600 Newton skier has more gravitational potential energy than a 500 Newton. Okay. Elastic potential energy. This is pretty cool stuff. As an object gains different types of potential energy when it is stretched, the potential energy associated with objects that can be stretched or compressed is called elastic potential energy. Okay. Rubber band, little rubber band gun, various things like that. We will watch a film when we get in, when we're talking about just different types of energy. One of them is that Smarter Every Day, where the guy does, and he goes to Germany where they actually, it's a slingshot factory, And they have all kinds of really cool slingshots. But one of the guys who works there was the world champion when they was filming this. If you ever paid attention, when you take a slingshot, you'll put something in the holder, right? And you'll pull it back, and you're aiming, and you've got it stretched back.
It was.
And you're losing, the longer you hold that back,
Yeah.
the more power you are losing.
Because, and I know it looks like.
Okay, it's losing electricity. So it's actually losing power. You'll watch this guy that's the world champion. He takes a ball bearing, puts it in his slingshot, and he's got his target set up. And as he's coming up, he's sighting, and he's like, bam, just that quick.
You hit it, right?
And he can, oh yeah, and he can put a ball bearing to a board. Okay, so it's pretty impressive. But he doesn't waste the energy. Okay, all right, get your hand out now. We'll go over it real quick. Okay. All right, so it's what is energy? The simplest definition of energy is the ability to do work. Again, your questions will come off of your handout, okay, not out of the book. Okay? Energy is is how things change and move. If everywhere around us, it's everywhere around us, it takes all sorts of forms. It takes energy to cook food, to drive to school, to jump up in the air. Everything is energy. Okay? Now, different forms. Okay, energy can take a number of different forms, and here are some of the examples. Chemical. Okay, a chemical energy comes from atoms and molecules and how they interact. Electrical is generated by movements of electrons. Gravitational, you have the large objects like Earth and the Sun that creates gravity and therefore gravitational energy. Heat. Heat energy is also called thermal energy, okay? And that comes from molecules of different temperatures interacting. Light is called radiant energy, and the Earth gets a lot of its energy from the light of the sun, obviously. Motion, anything that is moving has energy, and this is also called kinetic energy, okay? Nuclear. Huge amount of nuclear energy can be generated by splitting atoms. Potential energy is energy that is stored. Okay, it's not moving, but it has the potential to move. In physics, the standard unit of measure for energy is the joule. Okay, they do have other forms that they call it kilowatt hours, calories. That's when you're losing weight, you actually are exerting energy, you're burning off fat, you're burning off calories, okay? Newton meters, thermos, and foot pounds. The law of conservational energy, okay? This law states that energy is never created or destroyed. We talked about this earlier in another lesson. It only changes from one state to another. So energy is never destroyed. One example is the chemical energy in food that we turn into kinetic energy when we're moving. Okay, so it will change from one form of energy to another form. Sometimes it would change into something completely different, different state, but it never goes away. Okay, it never goes away. Energy cannot be destroyed. Yes, Caleb?
Wait, do you mean like wheat into bread?
Do what?
Do you mean like wheat into bread? Oh, thank you! How do we turn, what does it mean by like we turn chemical energy in food into kinetic energy?
When you eat it, you're fueling your body. Food fuels your body. That fuel gives you the energy to move.
So when you eat it, you turn it into kinetic energy.
Yeah, you turn it into energy.
Okay.
Yeah, that energy, yeah. That bread becomes energy, yeah.
It's not like when you have the ingredients and you turn it into the food. It's not like that.
It can be. It can be. I mean, it can be, that can be energy, and then it becomes stored energy until you eat it.
Or
Okay?
potential energy.
Or potential energy, yeah. Renewable and non-renewable energy. As humans, we use a lot of energy to drive our cars, heat or cool our homes, watch TV, and more. This energy, of course, comes from various places in different forms. Conservationists classify the energy that we use into two types. You have renewable and non-renewable. Okay? Non-renewable energy uses up resources that we cannot create, like natural gas or anything like that. We can't create that. Okay? But once we use it, it has the gas in your car. Okay, you can't, once you burn out a tank of gas, you can't get that tank of gas back. It's gone as far as being a gas that will power your car. But as it powers your car, it's transforming into something else, and it leaves your car in the form of the exhaust. Okay? So it doesn't, we talk about we burn gas, but it's actually, it's being changed into something else. So it's never gone. You just can't, you'll never be able to.
Then it goes into the cycle.
You'll never be, it goes up into the air and becomes various things. But you can never use it again to power your car, but it did not go away. That's what they're trying to say. Yes?
Wait. Yeah.
Leo's got a question.
Sorry. Okay, so and how you said the gas would actually go into like air molecules and stuff.
Mm-hmm.
Would snow be a solid?
It can be when it freezes.
Yeah, it'll be ice.
Yeah, it's ice.
Yeah.
Yeah.
'Cause I was
Okay.
confused.
So, anyhow. So remember, renewable is like wind, solar, things like that. Okay?
Hydropower.
Non-renewable is like gas for your car, things of that nature. Okay. Fun facts about energy: in 2008, about 7% of the energy used in the United States was from renewable sources. A modern windmill or turbine can generate enough electricity to power about 300 homes. The problem is it's got to be somewhere where the wind is constantly blowing. Okay. Otherwise, it doesn't work too well. People have used water powers to grind grain for over 2,000 years. Geothermal power is used energy from geysers, hot springs, and volcanoes. This is one, I like this one. The entire world could be powered for a year. The entire world could be powered for a year from the energy from the sun that falls on the Earth's surface in 1 hour, if we could just figure out how to harness it. So there's your challenge for you as you grow up. You can be the people that saves the world. Okay?
Yeah, that could stop. That could stop the.
Hope you enjoyed that, and we'll see you later.